Good morning. Well, I'm saying morning. It's early morning, really early when I'm recording this. Um, so this is the torque lecture that you are supposed to be watching and taking notes on before I see you in class on Thursday. Just FYI, if you're following along with the guided notes, I'm skipping kind of the middle section with rotational kinematics because that can be a little bit trickier conceptually, and I think it's better done in person. So we'll do that in class together on Thursday. So if you're following my PowerPoint, I'm picking up, I don't know what slide I'm picking up on, but about 2/3 of the way through, the first slide will say like, why is torque important or something like that. So that's where we're at. So we're going to pick up this concept of torque, and hopefully on Thursday be able to problem solve and put this all together with rotational kinematics. Okay, so rotational kinematics, again, what we'll do on Thursday, and torque, what we're working on today, is kind of our segue from uniform circular motion into more general rotational motion. So uniform circular motion, as we keep hitting home with, is a rotational motion in which an object is rotating with a constant speed. So it's going to be rotating with a constant speed, constant radius, constant centripetal acceleration. And that centripetal acceleration, remember, is also called radial acceleration. Now, if something is spinning, I need to grab a marker, wait a second. I apologize. So if something is rotating, let's say that it's rotating clockwise. Hopefully you can kind of see those arrows. Okay, so something is spinning clockwise. And if we look at, let's say I'm going to just look kind of at the top at this point, whether it is in uniform circular motion or a more generalized rotational motion, it's always going to have that centripetal acceleration. So it's always going to have an acceleration that's pointing towards the center, which kind of binds it in that rotation. Okay, so centripetal acceleration is always present. It's not necessarily always constant. This is stuff we'll talk about more on Thursday. So I'm dabbling in the kinematics a little bit. But this kind of acceleration must always be present for something to rotate. In a generalized rotational motion, it is possible, often happens, that you can have another kind of acceleration. So tangent to the circle. I'm drawing it tangent at the top going right. It could be going left. And this tangential acceleration is sometimes present. And it's something we're going to work with on Thursday, so we'll talk about how to calculate it and exactly what it means. But for now, let me say this. If something has a tangential acceleration, that means they're no longer a uniform circular motion. So this would be not UCM. And it means that the rate at which the object is rotating, the rate at which it's spinning, is either speeding up or slowing down. Okay, so if you have that tangential acceleration, the rate at which the object is rotating is speeding up or slowing down. Now, how does that tie to torque? In order to change the rate at which something rotates, you have to have a force that's doing that. And that force, we would say, causes something called torque. Okay, so torque is kind of the rotational equivalent of force. They're not the same thing. Definitely not the same thing. But it's similar. So torque is very similar to force. And if you have torques, those torques are going to cause rotational accelerations. Okay, so now if we're kind of following along the PowerPoint. So far, when we have been working with objects in the forces and doing free body diagrams, we have not cared about the location of the forces. So I'm kind of stepping way back here. And instead of showing you something that's actively spinning, let me just go through a free body diagram of something we worked with a lot in the last chapter. And that would be dragging a box or an object horizontally across the ground. Okay, so if I draw a free body diagram for that, I've got the weight down, I've got the normal force up. I'm probably pulling, it might be even at an angle, but it's going to be more up towards the top of the object, right? You know, assuming the object is to my waist height or even smaller, I'm not going to like bend down and get perfectly horizontal. So I'm pulling from somewhere up, and the friction is going to be all the way down at the bottom of the object, right? We've already talked about this. It's because the friction is caused by the interaction of this mass with the surface that it's acting on. Okay, so up until this point, when we've been calculating these accelerations, we've been treating these objects like point particles, meaning we don't care that there's a difference, like a clear vertical difference in the positions of these horizontal forces. We just say things sliding horizontally across the floor. Now, if you've ever pulled something horizontally, if I don't have something good here, sorry. I don't know how well you can see this, not very well. If I'm pulling this chair, just if you kind of watch the top part of it, it's on carpet. Down here is thick, shaggy, high friction carpet. And if I pull this, you can see right away, right, what happens. The chair, right at the beginning of that motion, just rotated about, you can't see it because I have it down on the floor, but about what we call an axis of rotation or a hinge. Now, this chair is not something you think of as a spinning object, right? But there was a tiny amount of rotation there. So by pulling it, I caused it to rotate slightly around the axis of rotation or the hinge. The same thing would happen here. So this point on the box, this is like my chair, would become what we would call a hinge point, and likely the entire box would kind of tip, so it would rotate slightly and then move. And so this is caused by this concept called torque. Now, torque can cause something to spin and rotate in a repeated manner, or even just this slight rotation, which is what we just saw with the chair, what we're talking about with the box. So these things are caused by torque. So torque, I'm going to define it in a second, but it's similar to a force. It's caused by forces. And it causes a rotational acceleration, whereas like a regular force would cause a linear acceleration. Okay, so let's go through the definition for what torque is. I just want to make sure I'm following along the slide. Did I get everything on the first slide? Wrong. I gave the example of a football tackle where on the person is the same idea as this. If this is a football player, he's a box, or he or she is a box, because I can't draw people. Again, they have their mass down, their normal force up. There's probably friction with the cleats on the field. Where somebody goes in on the body for the tackle, like whether it's higher or lower, changes how much the body of the player can rotate, which can be important if you're talking about a couple of yards. So these can be dirty hits, but generally a hit that's lower on the body is going to cause the person to rotate less, and we'll talk about that in a second because I'll give you the equation. So they'll drop faster than like their full height, going for a couple extra yards depending on how tall they are. 1 extra yard probably. Okay, so that was the example on the PowerPoint. It was football. All right, so let's go through the definition of torque. So torque has a Greek letter, tau is what it's called. It's just like a kind of goofy looking T. And it is equal to, the way it's written in the book, it's force perpendicular times R. Okay, so let's like run through what that means. First of all, torque, when you're calculating it, it's going to be a force in newtons and a radius that we want in meters. So the units for torque is Newton times meters. So I'm going to get into the concept of what force perpendicular means. R is the position where the force occurs. So the distance away from what you call an axis of rotation. And torque can be positive or negative. Now, there's one way to find this positivity or negativity using something called the right-hand rule, which I think I'm going to show you just for kicks on Thursday, but you can get away with never using it. It's more of a college level thing. Or you can think, if a rotation caused by a force would be in the counterclockwise direction, then we're going to call that torque positive, just a rule. So if a force would cause a counterclockwise rotation, then we say it has a positive torque. if a force would cause a clockwise rotation, it's going to cause a negative torque. Okay, so let me show you what I mean by all of this. So if I have an object, we're going to use a door as a demonstration. If you go watch the demonstration video, I'm making it separate because I have to go upstairs to make it. I don't have the door down here. But if this is a door and this is the doorknob, so I'm looking at it from the top. Okay, so this is my doorknob, and this is going to be my, over here on the left end, the hinge. And you'll hear me repeat this as I walk through it in the demo upstairs. But what I'm saying here is that torques, which cause rotations, they are caused by forces perpendicular to a surface happening at some distance r away from the hinge point. So r is your distance from the hinge point. Now, generally the hinge point is obvious. In your first year of physics, it's going to be given to you, so you're not going to have to figure out what it is. But as long as it is carried out consistently, you can call the hinge point any place on an object. I'm not sure if that makes sense yet, but I'm hopeful that next week you'll see an example of that. Okay, but for the door, there's an obvious hinge point, like where there's a literal hinge, and you can see that a door would spin about that point. So that's the place we'll choose. And what I mean by perpendicular forces is this, and again, you'll see it on the video, but if I come into the door and I lean, I push or pull this way, just like right on the edge of the door, it's not going to rotate at all. It's just going to stay still, right? I'm just pushing against the hinge, which is going to push harder against me, but the door is just going to stay still. If I come to the face of the door, so if I push this way or if I push this way, that's going to cause that door to spin. So it's these perpendicular forces that cause the torque. If you had angles given, you would want to find the y component, the vertical piece of the force that would cause this rotation. Okay, so that's what I mean by force. And by r, I mean the distance from this axis of rotation. So like this is 1r, I could call it r1, and then I could have a different force over here, and it's called r2, right? And so what we see is the bigger the force, the bigger the torque. That makes sense, right? Have you ever slammed a door in anger, perhaps? More force, more rotation. But the other thing we see is that the larger the r, the further away you are from that axis of rotation or hinge point, the more torque and the more rotational acceleration you'll have. Again, think about a door. You'll see me do it. But if I push over by the hinge versus out by the doorknob, you're going to experience a very different rotation. Okay, so that's how we calculate torque. So to find it, we're going to do a sample problem here in a second. It is truly plug and chug. We take the perpendicular force, we multiply it by r. That's it. What we do have to think about, though, is this direction stuff, so positive or negative. So let's look at this as an example. If I look at this first force, so we take torques one at a time. I'm not going to look at any other forces. I'm just looking at this first force. If this force, which I have drawn pointing down, causes the door to spin, the door is going to spin. Let me try and give it a different color. The door is going to spin in this direction, right? So I'm ignoring the other force. And that direction is clockwise. So since this force, the first force, would cause a clockwise rotation, we would call this torque negative. The second force, this one, if we look at this second force, and again, I'm going to ignore the first, so I pretend this is not happening. And I think, okay, the second force, if that's the only thing acting on the door, how's it going to spin? Well, the door is going to spin up this way, right? Which is counterclockwise. So we would say that the second force causes a positive torque. All right, so let's do that with a practice problem, actually with spinning doors. Let me find my eraser. And see if it's comfortable for you, hopefully. Okay. This is the last slide. Sorry, I had to find my spot. Battle of the revolving door is the problem that I'm looking at. So this says, two disgruntled businessmen, their behavior is so stupid, so I made them men. Two disgruntled businessmen are trying to use a revolving door. The door has a diameter of 2.6 meters. The businessman on the left exerts a force of 625 perpendicular to the door, 1.2 meters from its center, and the businessman on the right exerts a force of 850 newtons perpendicular to the door, 0.8 meters from the center. Find the net torque on the revolving door. That's a lot, but hopefully you have the problem in front of you and you're copying it. So I say men because I could totally picture my brothers doing this. In fact, I think I've seen them do it downtown. So if you, if you're ever downtown in normal times, spinning doors, that was always fun when I was a kid. So you get a revolving door, and ideally people are nice and everybody's going in the same direction. It just kind of keeps revolving. But you could, if you've ever done this, get into a place where you're pushing in a way that you're basically fighting each other and seeing who wins. That's what this is. Okay, so businessman 1 pushes with a force, so I'll call it force 1, of 625 meters perpendicular to the door, 1.2 meters from its center. So that's going to be the radius. And we're going to draw that in a second. And then businessman 2, so let's call this force 2, pushes with a force of 850 newtons perpendicular to the door, 0.8 meters from the center. Now, this actual problem came with a picture that I did not put on the slide. So they didn't, in the picture they show us which way these forces are. So I'm going to kind of sketch that out. The entire door is 2.6 meters. So let's just say that it's 2.6 meters, which means from the center to each end is 1.3 meters, right? Okay, so here's the picture that actually came with this. Force 1 is 625 meters, and it is 1.2 meters from the center. So this radius is 1.2. And then force 2 was on the other side, 850 meters. And it was 0.8 meters from the center. Okay. And so the question is basically who gets the door to move? So we want to find the net torque. And if we can find the net torque, that will tell us what direction this thing is rotating. So there's two torques, torque from force 1, torque from force 2. To find those torques, I'm going to ignore the direction for right now. Super simple to find the torques. So for torque 1, it's force 1, 625 newtons. What am I rating meters? We're low. Times 1.2 meters. And for torque 2, it's 850 newtons times 0.8 meters. And so when we plug that in, I get for my first torque 750. Again, I'm not dealing with the sign yet, okay? So I'm just kind of writing it as positive. And for the second torque, I get 680. Okay. Now, let's go look at the sign. So, for the first torque, the one on the left, if the force on the left causes the door to rotate, the door is going to rotate in this way, right? Again, I'm not looking at the second force, I just look at one at a time, so don't think about what else is going on. So if the first force were the only force to act on the revolving door, and here is our axis of rotation, right in the middle, then the door would revolve in a counterclockwise direction. And so we would say this is a positive torque. Okay, the second force, so I would erase or use different colors. The second force, if the second force were the only force acting on this door, the door is going to rotate in this direction, right? Which is clockwise. So we would say the second torque is a negative torque. Okay, so to find the total torque, we simply add the 2. So it is positive 750, negative 680, which gives us a total of positive 70 newtons times meters. Because the torque is positive, this tells us that the door is going to spin in the counterclockwise direction. So the net torque is positive, it's positive 70. The door is going to spin in the counterclockwise direction, which means this guy over here on the left wins, if we're going to get it to go counterclockwise. Okay, so that's an example of torque. We'll wrap it up Thursday when we go through rotational kinematics, and then hopefully you can get into some of the problem solving without issue. We'll do one more problem on Thursday. This is a little bit trickier, just to make sure we're on the same page. But calculations wise, it's very simple. The place where you have to give it a little bit more thought is when you figure out the directions for that rotation, and then think about kind of like what's going on here conceptually. So how does this relate to force, and how does it relate to radius? All right, I'll stop here.